Alright, welcome to part A of module 2. This is single area OSPF, and what we'll be doing is just concentrating on version 2 of the protocol and how it works and how to configure it. Now this is a two-part, as the original presentation is quite large and would make for an extremely long recording. So I've broken it up to deliver. So let's look at what we're doing in this particular video. So we'll be looking at what OSPF uses for its ID system, how to set up point-to-point networks within OSPF, and how to configure a multi-access network. So to do this, we'll need to explain a few things on how that works, and I'll leave the details until we get to the appropriate points. Alright, so router ID. When we have multiple devices talking to each other in a topology, we need to be able to identify which device is talking to each device. So this is where router ID comes into play. Now, for us to give you an example, we have this reference topology, and it's going to be a simple 3-router topology. We're using a Loopback interface on router 2 to simulate our connection to the internet, and we're also using Loopback interfaces to simulate our connected local area networks, just to make life easy while we're doing these examples. Now we're going to be using area 0, which is the backbone of the OSPF protocol. All other areas have to join area 0, but that is not covered within this series, as we're only doing a single area. Behavioral changes of the protocol as you add different areas will be covered in the advanced OSPF areas, which, if you decide to do the CCNP courses, you'll get into that there. So within the config, we have the router process, and in this case it's router OSPF, and then we follow that with the process ID. We can have multiple instances of the protocol running on the same device. This is why we need to identify which process we're configuring. Why would we want to do this? Well, when we set up multiple areas on routers that share resources, but we don't want them to share routing information, we want them to run as different instances. It's not very many occasions that I can think of off the top of my head where you want to do that. As a local administrator, you'd want to be able to get access to everything, but if you're running a large organization and have it segregated into specific access using your protocols, that's one way you could do it. So within the configuration, you'll notice here that after we type in the routing command, we go into the OSPF configuration parameters for this instance. So we can configure the area, the auto cost, default information, you can read the list. So there's lots of specific commands that apply to OSPF and the router command. Now, we will cover setting up the networks in both the original way of doing the network command and the new way which came about with version 3 during this course. So to start off with, we'll cover the router's ID. So we need to identify each device within the OSPF domain, and we do this with a unique 32-bit value, which is equivalent to the old IPv4 address. Okay, and it's represented in the dotted decimal format. So, and we actually will go through and see the preferences or default ways a device will come up with this ID if you just leave it to its own device. So, as we said here, or it says here, we can leave it to its own and it will automatically assign itself an ID, and it does that by looking at its own interfaces and taking an appropriate IP address from off its valid and active addresses. So why do we need to have an ID? Well, as I said, we need to identify each device, because when we want to exchange information between these devices, they need to know where that information is coming from. So we need to be able to synchronize all the databases between all the devices, and they need to know what device is the boss when we have a multi-access network, which we'll get into in a little bit. But basically we have a boss router within that election, and it's known as a designated router. So in this environment, the ID of that device needs to be known by all the other participants within that multiple access, and they need to refer to it as it pushes all the relevant updates out of that device. So it controls the information for within that environment. So how does the device choose its router ID? Well, the first option is for it to be administratively configured within the router ID format. So this is where the administrator decides to give it the ID. If that isn't configured, the router will then choose the highest address that is configured on a Loopback interface. If it does not have any Loopback interfaces configured, it will then choose the highest IPv4 address from any of its configured and active interfaces. Now, one of the little things or problems we have on that point 3 is if that router ID is chosen via an active interface, and for some reason that interface becomes inactive, so does the routing process, because it no longer has a valid ID. So it's best practice to manually configure your device. So just a refresher, just in case you've forgotten how to configure a Loopback interface. It's done the same as every other interface, we just go interface loopback and then the interface number. Put in the IP address. They are always active as a loopback. Okay, so the only time a loopback is not active is when the router is no longer active itself. So if we now exit out of that and use the show IP protocols and include the router ID, we now see it's chosen the ID to be the loopback address. Now, this process will be process as in which ID it uses. It chooses that when you start the process. Okay, so get all your interfaces and all that pre-configured, and then come in and do your routing protocols, how you should be doing it. So if you want to configure it manually, you go into the router instance and then use the command router-id and then type in the ID. Now within our example topology, we're going to use quad 1, quad 2, quad 3 for the 3 different routers. So you can modify the ID, but basically you will need to clear the process, in other words restart it. So what you need to do is use the command clear IP OSPF process and then confirm that you want to restart, and this will remove all your adjacencies and re-establish your neighbors and restart using the new ID. So all that information and synchronization of routes and everything have to reoccur, as it needs to re-establish communications with its neighbors using the new ID. Section 2.2 is our point-to-point networks. So we can specify our network in the instance, so router config-router, and the command is network, so we're now specifying connected network to the process. We put in the network address. OSPF uses a wildcard mask, not the subnet mask, so it's the inverse, and then the area and the area ID. So in our examples it will be area 0, and just a reminder on how to calculate a wildcard mask. Put 255, 255, 255, 255 down, and then your subnet mask underneath it, and you subtract the subnet mask from the 255 top line, and that converts your subnet mask into a wildcard mask. So for an example, 255, 255, 255.0/24 would end up as 0.0.0.255 as a wildcard mask. And this is an example. Now, unfortunately, the original slides had a bit of a typo. So here you'll notice, okay, so here's our quad 255 with our /24 255.255.255.0, and we end up with the new wildcard mask following that. So the next example was a /26, which is 255.255.255.192, and you subtract that and you end up with 00063. Alright, so just as a reminder of how to calculate those, yes, I know that in some of the newer iOSs, if you type in clearly a subnet mask, some of the newer iOSs would actually convert it on the fly for you, but don't rely on it, because you will come across older devices which will have no auto conversion within it, and you will misconfigure your network. So next we have our network command example. So under the router OSPF 10, we go through and list all the networks that are actively participating within the process. So all of our interfaces would be listed as a separate network command. So if you've got 3 connected networks, you should have 3 network statements. Alright, so the advantage of using quad zeros as the wildcard mask, you actually identify specifically the interface, okay, and you don't have to do the wildcard calculation. I don't think most people would have a problem, but again, this is not necessarily available on the older versions of operating systems out there, so approach with caution. Certainly works with all the newer equipment, okay, and it will actually come up with this format as IPv6 uses this. So definitely any operating system out there on the Cisco area that supports IPv6, which has been around for a long time within the versions, will support this idea. Okay, so the other way of configuring the process, which came about with the version 3 adaptation of it, because of the way we do routing protocols under IPv6, we can now, rather than having individual network statements under the routing process, we just start the routing process and then go to the individual interfaces that we want to participate within the routing process, and we tell it to join the process. So the command on the interface is IP OSPF process ID. So in this example, it's IP OSPF 10 area 0. And this will tell the routing process that this interface is an active participant within the routing process, and it does all the necessary calculations for advertising that network for you. So you don't have to worry about doing those wildcard calculations or any of that. Now, there's many reasons why we would want to advertise a network but not necessarily send updates via that network. Okay, so for example, if we are advertising our local area network, but there are no other routers within that local area network, it's only host or end devices, we don't need to send routing updates to those devices. It poses a security risk. So we want to be able to limit where our updates are being sent. So that's one of the reasons we might want to have a passive interface. Another one is bandwidth and resourcing. So if we are only one way in and out, for example, you might want to limit where updates are being sent. If it's on a very slow WAN link, you might want to limit your bandwidth consumption on that slow link. And the last one there, your resources. You might want to have old legacy devices still within your network that may not have the same amount of resourcing available, so you might want to put that in a passive mode, for example. So how do we make interfaces passive? Well, we go into the routing process and use the passive interface command, and then we specify which interface we want to be passive. And what this does is it means that interface will not send routing updates, so it won't actively transmit OSPF protocol packets down that interface. It will still form and advertise the appropriate statements for advertising the network that is on that interface. It just doesn't send the hello packets and that out of that interface. So within the process of a point-to-point network, we do not have to have an election for it to decide who's the designated router and who's the backup designated router, but it does have to decide which one's going to talk first. In other words, send its updates. So within every Ethernet interface, we have the default of being a broadcast. All right, that's just Ethernet. Now, if we only have a single other device within that area of broadcast that actually is the recipient of the protocol, we don't want to broadcast it to everyone. We want to actually form a link directly to that other device. So we need to take a few different steps to make a point-to-point network within this environment. So if we look at the OSPF interface command, so within the show IP OSPF interface and specify the interface, or else you'll get all of the interfaces, which is information overload. Things we're looking for is, as a general rule, is our IP address, the area we're attached to, what the process ID is, the router ID, and here in the yellow we're looking at the type of connection it is. So by default, Ethernet is broadcast, and the cost is calculated based on the speed of the interface, and we'll talk about how we can influence the costing of our interfaces a little later. But if we look down a little bit further, it will tell us the ID of our designated router and our backup designated router, and what the IP address is that we can communicate with them on. And following that, we have our timers. Our timers need to be the same. So 10, 40, 40. So these two are the two main ones we set, hello and dead. So all of our participating devices need to have the same timers, as you would have heard when we went through the theory behind OSPF. Next is how we configure or change that network type from broadcast to point-to-point. So we go into the interface that we want to configure as a point-to-point, and we configure it with IP OSPF network point -2-point. So what this does is it disables the election routine, because as a point-to-point, there is only one other device that it needs to send the information to, and it doesn't need to do an election. So we're saving resources and speeding up the process, and it also changes the way it communicates. So loopbacks will come up within our configuration of our networks as a /32 network. Now, this stops us using it as a full subnet. Okay, instead of being a /24, for example, it will only come up as a /32, so it will only have one valid IP address. So if you went to ping this with any other IP address, it would fail. So when we want to use loopbacks to simulate more networks, we go in there and use the network point-to-point command, and that will advertise that loopback interface with the configured subnet that was used when we put in the IP address. So that means all the addresses in that range are now valid, and you'll get a ping response from those. So it's quite useful when we want to use them as a de facto interface, live network, and we can set up and test policies and that we want to apply to the network using these phantom networks, and see how the traffic is affected, and then convert those statements into live production statements. It's just one of the things you can do. MultiAccess OSPF. So this is where we have more than one device communicating with the router. So you can see here we have our 4 routers interconnected via a switch. So we're using a broadcast, and in this scenario, in this environment, we need to have an election. So this is a multi-access environment, and between these devices, they need to determine who's going to be the one controlling updates, and this allows us to have efficient communication between all the devices and limits the impact of changes within the area. As far as flooding out various updates and link states and so on and so forth. Now, we need to have an election. Now, the election determines who is the designated router, and then after that's confirmed, there'll be a second election confirming who's the backup designated router. So whose role is what? So the designated router is the one that collects and distributes all of our updates. So our link state advertisements are sent and received, and this information is being communicated on 224.0.0.5. Now, the backup designated router is there, and it's just listening at this stage. So it's keeping track of all the above information, but if it doesn't hear from the designated router within the appropriate time set based on the hello packets, it'll take over the role of designated router. So basically, if it hasn't heard from the designated router, it assumes it's failed and will take over that role. You will then have another election to elect the next backup designated router. Now, all other routers, except for those two, are known as DR other. This means then neither the designated router or backup designated router. And they are using 224.0.0.6 to send their packets, their LSAs, to the designated routers. So only the two devices, DR and BDR, will listen on the 0.0.6 multicast address. All devices listen on 224.0.0.5. Okay, so 0.0.5 is where the updates are sent from the designated router to all members of that environment. 0.0.6 is the updates being sent to the designated router so that it can compile and send up one update. So the designated router is responsible for collecting and distributing all the change notifications. So within our reference topology, we have our IDs. Now, based on our IDs and our election process, we have a designated router that is going to be the highest IP address within that multi-access. Okay, so we have three interfaces all joined together on a switch, so therefore it's a multi-access broadcast environment. Election will take place. 333 is the highest ID, so it'll win the election. The secondary election will elect router 2, as it's got the second highest ID as the backup DR. And router 1 will just go to DR other. So how do we confirm that election process has occurred? With the show IP OSPF interface, as we looked at other earlier, we'll see that it will tell us who the designated router is, who the backup designated router is, and it'll also then tell us who our immediately adjacent neighbors are. Now in the example, we're looking at router 1. So we have 2 adjacencies with routers 2 and 3, which happen to be our DR and BDR. And if you go to router 2, you'll see a slightly different output. And in here, we can see that router 2 is a BDR, and its adjacencies are router 1 and router 3. Router 3 is the designated router. And if we look at router 3, it states it's the designated router, and then it has adjacencies with 1 and 2. So another way of looking at the adjacencies is using the show IP OSPF neighbor command, and this will give us the neighbors and their states. Now, when we're looking at the stage of communication, we should have full. Any other statement, we could possibly have a stuck process. In other words, forming the neighbor relationship takes place very quickly under normal circumstances. So the two-way communication should not be there under normal circumstances. So you should either have full DR other, full DR, full BDR statements. The only exemption where you would have two-way is in multi-access broadcast networks. Okay, so just be aware that you need to know your network type so that you can understand where the communication states should finalize to. Okay, you need to understand the relationships between the neighbors and where they go to in communication states under normal operating procedures so that you can troubleshoot. So it's kind of important. So when we look at this command and we're looking from router 2, we'll see that it has a neighbor of 1, which is full, and the state of its neighbor is DR other, and then neighbor 3 is full and its state is DR. So it's basically telling you that it's got full communication back and forth, it's exchanging all of its information, and also telling you the state of the relationship between the two devices. So the election process is very set. It follows the same steps. And the highest interface priority will be elected as the designated router. So the second highest interface will become the backup designated router. Now, what's a priority value? Well, it's a random, well, I won't say random, it's a value between 0 and 255. If you don't want the device to participate in an election, such as a old router that doesn't really have the processing power to manage all those communications, you would change priority value to 0, so it no longer takes part in an election. The default on multiple access interfaces will be 1. Now, if you want to influence the election, you would then turn around and change that value to a higher value. The higher the value, the more likely it will be elected the DR. If all the values are equal, in other words, their default values, it will use the router ID as the election decider. So the ID is crucial to determining who's elected. Now, once the election takes place, that's it, it's done. It doesn't redo an election. Once more devices join in, they just get told this device is the boss, the designated router, and they move on. The way you have to force an election is basically close down everything and then restart them. So you restart them in the order. So you start up your designated router first, your backup second, and then the others. Okay, so it's not something you really want to do in a production environment unless you really have to. So when does an election occur? Well, when the DR fails. Why does it do an election? Because the backup designated router becomes the designated router, and it needs a new election to find out who's going to become the BDR. Alright, so that will occur. If the OSPF instance fails or stops, and that's the same as it failing, so the backup becomes ta-da. So again, multiple interface. So if this shut down the interface, it no longer can participate. It can no longer do the functions of designated router. So all of those 3 lines basically are saying the same thing. For whatever reason, the designated router fails to communicate to the other devices within that broadcast environment, an election occurs because the BDR will take over. Now, once that original DR rectifies itself and comes back online, it doesn't take over the role of DR. It just becomes another device. Alright? It's just done. So priorities will affect who's elected. If they are all at the default and equal to all the devices, the router ID will determine who's elected. So a better way of controlling this is using the priority value, and we go to the interface that is part of the election, and we type in IP OSPF priority and the new value. This will influence this device's participation in the next election. So this is how we would do it. We want this router 1 to become the boss, the designated router. So we change the priority to 255 and restart process. And that brings us to the end of part A. Please tune in for part B. hope you have a nice day, and I'll see you in the next part.